Welcome back, everyone. So it's a pleasure to have Sanchayan Sen, who will speak about long-range percolation on the hierarchical lattice and discrete torus.
Thanks to the organizers for the invitation. Always good to be here at ICTS. I want to talk about the nature of the phase transition in these two models. So the first one is long-range percolation on the hierarchical lattice. The other one, the discrete torus. So first, the most basic example of phase transition is that of the Hierarch random graph. The Hierarch random graph, GNP, is where you have n labeled vertices, and you place edges independently between each pair of vertices with probability p. So this is the graph. GNP, the Hierarch random graph. Now, this is a classical result that this random graph goes to a phase transition around p equal to 1 over n. So let's T1, the largest component in GNP over n. Then when t is less than 1, that's where this graph is in the subcritical regime. So here, the size of the largest component, like a constant times log n. Constant depends on t. And when t is greater than 1, the size of the largest component in like a constant times n. So here it was log n, it was order of log n. Here is order of n. So there's this phase transition as t passes through 1 over n. And exactly when t is at 1, or rather around 1, that's when you get the critical window. That's where this graph exhibits critical behavior. And here, the size of the largest component is of the order of n to the 2/3. In fact, the size of any ith maximal component in this regime inside the critical window is of the order of n to the 2/3. And there was this very precise result proved by Aldous in 1997. He showed the following. So he showed that if you look at the Hierarch graph, Gn, the connection probability is now 1 over n plus lambda over n to the 4/3. We're inside the critical window. Then let Ci denote the ith maximal component of this random graph. Then the sizes of Ci scaled by n to the 2/3. This entire sequence converges in distribution to some limiting sequence. Let's call this Z lambda. And this object Z lambda as a process in lambda, this is called the standard eternal multivariate Follow-Sum. This was a very influential work by Aldous, and it introduced a systematic study of the stochastic process called the multiplicative Follow-Sum, also a central object. Okay, so now this result, this is something about the sizes of the maximal components, and the sizes like n to the 2/3, and it also gives you the scaling limit. Right? Then there was this work by Luigi Atariberri, Nicola Puta, and Nicole Schmidt. So they improved the scaling limit about the sizes to matrix space level convergence. So what they showed is the following. So again, you look at this critical Hierarch graph, and you view the components as matrix measure spaces by using the graph distance, and you endow it with the counting measure on the vertices. The graph distance on each component gives you the matrix, and the counting measure on the vertices, that gives you the measure. Then what they showed is that if you view the components as random matrix measure spaces, then these matrix measure spaces with the distance as scaled by n to the 1/3 and the measure scaled by n to the 2/3, so that now converges in the Gromov-Foster-Prorov topology to a sequence of lambda limiting random matrix measure spaces. So this Gromov-Foster-Prorov topology is a way of comparing, is a way of measuring the distance between two matrix measure spaces. So the Gromov-Foster distance is a way of comparing two matrix spaces. The generalization of that is the Gromov-Foster-Prorov distance that compares two matrix measure spaces. So in that topology, the sequence of random matrix measure spaces converges in distribution to some limiting sequence of random matrix measure spaces. I'll just call this limiting sequence as grid. This will be a notation for this talk. In the same paper, they give a depth first construction of these limiting spaces. And in the companion paper, they give a core decomposition of these limiting spaces in my lambda. And we also have this equivalent breadth first construction. So these spaces, they have several equivalent constructions. So because in this talk, we're not going to go into the details of the proof, so I'm going to skip the exact construction of the spaces in mind. Locally, at most points, they look like the Brownian CRT. So locally, they look like Brownian CRT. but they also have a random number of cycles. It's a semi-lambda, they're locally, basically like Brownian CRT. So there's of course a random number of cycles. It could be 0, it could be 1 with certain probability. So this limiting sequence, the sequence of random matrix spaces, crit, this is the candidate for the scaling limit of a very large number of models of discrete, random discrete structures. And I will say that a model is in this universality class, the Roshan universality class, or the Brownian universality class. If the model goes to a phase transition, and around the point of phase transition, there's a critical window where if you look at the components and you view them as random matrix measure spaces, then they have a scaling limit, basically a rescaled version of this sequence grid. If that happens, then I'll say that that model of random discrete structure belongs to this Roshan universality class, or the Brownian universality class. So some known members of this universality class are these. So you have the inhomogeneous random graph, or the kernel is multiplicative, or a graph with given degree sequence, and as a consequence of that, you also get the same kind of behavior for the vacant set left by random walks on random regular graphs. So this model, H-weighted graphs that converge to an L3 graph in a certain topology, that also belongs to the same universality class. And more recently, there's been this work, bond percolation, critical percolation on the hypercube. All these models are now known to be in this universality class. So so I'm calling this the Brownian universality class because the limiting spaces, locally like the Brownian CRT, in fact, these spaces in my lambda, they can be constructed by starting from a Brownian CRT, starting from a tilted Brownian CRT. There are also other universality classes where the scaling limit is non-Brownian. And there's been several works trying to identify these other universality classes that arise naturally studying random graphs where the vertices, so there's a strong inhomogeneity in the roles played by the different vertices. So for example, graphs with given degree sequence where the degrees have a heavy tail. In certain cases, in models like that, the scaling limit turns out to be non-Brownian. In fact, they can be constructed in terms of something called inhomogeneous continuum random trees or in terms of Lebbe trees. Okay, so in this talk, we'll mostly focus on the Brownian universality class. At the end, I'll briefly come back to this other universality class. Okay, so this is the first model that we're going to study. So in this talk, we're going to study two models. The first one is the discrete torus. So here you fix any dimension, e greater than or equal to 1, and pick an integer n greater than or equal to 2. Then you consider this equivalence relation on ZD, where x is equivalent to y, if x minus y is a member of NZD. Right? And then look at the discrete torus, it's just ZD quotiented by that equivalence relation. Or equivalently, you can look at a large cube, and then you put periodic boundary conditions on that. So let's take the discrete torus. So I'll use this notation, norm x minus y. So this is just going to be the L infinity distance on the torus, on the discrete torus. Now this is the random graph that I want to study. So take any kernel kappa that's radially symmetric. So by that I mean that kappa xy is some function of norm x minus y. And then we look at this random graph where we place edges between x and y independently for each pair of vertices x, y in the discrete torus with probability 1 minus exponential minus kappa xy. Start with the discrete torus. You construct this random graph where we place this independently, or we place the edges independently between each pair of vertices with these probabilities. And let Ci, the ith largest component in the resulting random graph. So we're going to focus on kernels that decay polynomially in the distance. But first, let's go over the known results on nearest neighbor percolation or spread out percolation on the discrete torus. It was predicted by Eisenman in the 90s that if you look at critical percolation on the discrete torus, it behaves similarly to the critical Roshan graph. And there's been a lot of work on percolation on the discrete torus. So these works are particularly related to the kind of things we're talking about here. So there were these two papers by Markus Heidenreich and Remco van der Hofstede, where they showed that if you look at the discrete torus, let's look at the nearest neighbor percolation on the discrete torus, or the spread out percolation on the discrete torus. So for nearest neighbor percolation, you take the dimension d to be sufficiently large. And for spread out percolation, the dimension d is greater than or equal to 7. And the spread is sufficiently large. If you consider those models and you look at critical percolation on that, then each critical maximal cluster is of the order n to the 2d over 3. So this is volume to the 2/3. The volume is n to the d, and the size of each maximal cluster, each critical maximal cluster is volume to the 2/3. It's of the order of volume to the 2/3. And the diameter of each critical maximal cluster of the order of volume to the 1/3. So this is similar to the Erdős-Renyi behavior. Remember, we had the scaling 1 over n to the 1/3 and 1 over n to the 2/3. So here we scale the distance by n to the 1/3 and scale the mass by n to the 2/3. So similarly, for the discrete torus, for critical percolation in the discrete torus with sufficiently large d, you have the same scaling for the volume and the distance. In this first paper, they had the upper bound right. So the upper bound was order of n to the 2/3. There was a log correction to the lower bound. Then they improved it in the second paper. And there was this work by Remco and Artem Shaposhnikov, where they showed that all long cycles in the critical maximal clusters for nearest number percolation in the high dimensional discrete torus is of the order n to the d over 3. So again, volume to the 1/3. So here, long cycles they have to be defined carefully. So in this paper, long cycles are defined as those with size of the order, with length of the order n. If the length of the cycle is at least, say, greater than n over 4, then we call that a long cycle. And what they showed in this paper is that if the length is greater than n over 4, then it has to be of the order n to the d over 3. So there is no in between. So of course, when you look at nearest neighbor percolation on the discrete torus, there will be cycles of length 4. So there will be many such cycles. There will be many short cycles, right? But there are only order 1. There are only the long cycles. They're all of the length to the 1/3. And if it's greater than, let's say, n over 4, then the length of the cycle must be volume to the 1/3. And the number of long cycles in each critical maximal cluster is also order 1. So again, here, the number of long cycles have to be defined carefully. The way it's done in this paper is you look at the minimal number of edges you need to erase to get rid of all cycles of length n over 4. Then that number, that forms a tight sequence of random variables. In that sense, the number of long cycles in each critical maximal cluster is tight. So this is again similar to the Erdős-Renyi behavior. So all this shows that if you look at nearest neighbor percolation or spread out percolation in the high dimensional discrete torus, then you get Erdős-Renyi type behavior. And the prediction, the conjecture is that the scaling limit should be crit, should be a rescaled version of crit. So in that sense, this model should be in the Erdős-Renyi USA class. So this is also stated as a conjecture in this CRM lecture notes by Markus Remco. So this problem, so this conjecture remains open. So proving the Erdős-Renyi scaling limit in the matrix sense or nearest neighbor critical percolation for the high dimensional discrete torus, this remains open. We're going to prove we're going to deal with long range percolation on the discrete torus, where the kernel decays polynomially and the exponent is in a certain range. I'll come to that in a minute. And then the second model is long range percolation on the hierarchical lattice. Let me define the hierarchical lattice first. So here again, you fix a dimension d greater than or equal to 1, and you fix an integer L greater than or equal to 2. And let omega LD be this set. So basically, any set with L to the power d points will do. But here we're taking it like this. So it's z quotiented by LC to the d. If you do it like this, then it's easier to write things like x plus y, x plus y. So you can compare the results for the hierarchical lattice with the discrete torus or BD. So let omega LD be this set. and let HLD be the hierarchical lattice, which is the set of all sequences, the set of all infinite sequences, where each entry is an element of omega LD, and after some finite I0, all the other coordinates are 0. Basically, there are only finitely many non-zero coordinates. So this is the set HLD, and let's put a norm on it. So we're going to define a distance on it. So for any sequence X in HLD, X, let's say X1, X2, X3 is a sequence, then we define norm of X to be 0 if Xj is 0 for all j. So if we have the constant 0 sequence, then norm X is 0. Otherwise, it's L to the power I if the ith coordinate is the last non-zero coordinate. You take any element of HLD, look at the last non-zero coordinate, that happens at the ith position, then you define norm X to be L to the power I. And norm of X minus Y, you take that to be the distance between X and Y. Right? So there's a natural way of defining X minus Y because we're writing things like this. So X minus Y is the pointwise, you subtract the coordinates pointwise, and norm of X minus Y is the norm of, just the norm defined like that. Let's also define lambda n to be this ball. So this is the ball of radius L to the power n around the constant 0 sequence. So lambda n is the set of all x in the hierarchical lattice. So norm x is the equal to L to the power n. Again, we construct the same random graph. So let's take any radially symmetric kernel kappa on HLD, and you place edges independently between each pair of vertices x and y with probability exact same thing that we had for the torus is 1 minus exponential kappa xy, and let Gn kappa now be the restriction of that random graph to the vertex lambda n. I'm taking a kernel kappa that's defined on the entire hierarchical lattice. You can connect any two edges x and y with this probability, do this independently, look at its restriction to the vertex at lambda n. So now I have a random graph on a finite vertex set. And again, let's Ci, the ith largest component on Gn kappa. So for the torus, so to construct the torus, we started with a large cube in ZD, and then we put PRD boundary conditions on that. So there's no need to impose a boundary condition here, so we just directly work with this ball lambda n, because lambda n, the way this is defined, this is already vertex transiting, so all the vertices have symmetric roles. So there's no need to impose an additional boundary condition. Okay, so this is a pictorial representation of the ball lambda 4 in H22. So the distance between any two of these points would be 2. The distance between any point here and any point here would be 4. The distance between any point inside this square and any point inside this square would be 8. Similarly, any point here and any point here at distance 8. And any point here and any point here at distance 16. So basically, it's the smallest square, so it's the smallest outline square that contains both points. So that's the distance between 2 points. Now, there's been some work on percolation on the hierarchical lattice. So there were these two earlier works where it was shown that if you take the kernel like this, there's some beta times norm x minus y to d minus alpha, where the exponent alpha is between d and 2d. So when the exponent alpha is between d and 2d, then it was shown in these two first papers that this model goes through a phase transition. So there's a beta c, that's a number between 0 and infinity, such that the model goes through a phase transition at beta equal to beta c. There is a unique infinite open cluster in the supercritical regime, and the percolation probability is positive. These were known in these two earlier works. More recently, there's been these two preprints, these two papers by Tom Hutchcroft. So in this first paper, he looks at the critical hierarchical lattice, and here the side bounds up to constants are proven for the 2-point function, the critical hierarchical lattice. And the second paper, this is a detailed study of critical cluster sizes in hierarchical lattice. So in particular, in this paper is the exponent for the tail of the critical cluster of 0 is determined. And there's also a tightness result for the normalized cluster sizes when alpha is between 4D over 3 and 2D. But there's no scaling limit. Scaling limit is missing. It was conjectured in this paper that when alpha is between D and 4D over 3, then this model belongs to the Hierarchian universality class. In particular, you have the Aldous type cluster size scaling, and then more generally, if you look at the components as metric measure spaces, then the scaling limit is correct. So that problem also remains open. You want to say something?
Question, sorry. For standard percolation, we've seen that there is a big difference between the behavior in the box and in the torus, right? The exponents for when functional volumes are different. Here, the right analog is what? What should I think about as an analog? Is the box or the torus for this hierarchical lattice?
So for, if you want to take the critical limit, then you have to look at the finite box, right? Because for the infinite, so if you look at the entire thing,
Should think as a torus, right?
yeah, so this you can, so lambda n plays the role of the torus.
Yeah.
Because the vertices, they all have the same role.
Okay, thank you.
So yeah, so they were saying that when alpha is between D and 4D over 3, so it was conjectured in this paper that this model belongs to the Hierarchian universality class. So that problem remains open. So what we're going to focus on the regime, where alpha is between 0 and D, and there we're going to study the critical behavior, and we're going to show that when alpha in a certain range, when alpha is in fact between 0 and 5D over 6, that's where you get the Hierarchian study. So, that's going to be our main result. So before we get to that, let me mention this equivalence of distances between the two models. It's a standard technique when you're studying percolation on ZD or on the torus. You break up ZD or the torus in, you break it up into different scales of exponentially increasing volume. So you consider cubes of side lengths that grow exponentially. Right? Now, if you consider such a decomposition of ZD or the torus, then for most pairs of vertices, let's take one vertex here in scale 3, and then another vertex over here, the distance between them is comparable to L cubed. For most pairs of vertices, you have this comparison. You have this distance equivalence that for most pairs of vertices, distance is upper and lower bounded by some constants times L cubed. Now, this is also what happens for the hierarchical lattice, right? If you have 2 points, one is within lambda n, and the other one is lambda n plus 1 minus lambda n, and the distance between them, the way we define the distance, is exactly L to the power n plus 1. So up to a constant, so these two distances, they're the same. The difference, so there is a difference when 2 points are very close, but for most pairs of points, you have this equivalence of distances. So this is why we do these two models together, because many of the calculations, because of this equivalence of distances, many of the calculations lead to the same upper bounds, and the proofs are quite similar. So one thing that's different is that the model of hierarchical percolation has radial symmetry, but the cubic lattice or the discrete torus, that symmetry is missing. So the spherical symmetry, the rotational symmetry is missing. So the steps of the proof for the hierarchical lattice that uses the rotational symmetry or the radial symmetry, so those have to be done differently. But all the other calculations, they are very similar and they lead to the same upper bound. So we'll study these two models together. Okay, so now let me state the three main results for these two models. So the first one concerns the phase transition when alpha, the exponent, is between 0 and d. So fix an alpha between 0 and d, and rho be a function defined on 1 infinity, and it decays like this. So it's equivalent to r to the power minus 1. So let Xn be this set. So it's either lambda n, so it's a large ball, a ball of radius L to the power n, or the discrete torus with n to the d versus Xn. You can take either of these two spaces. Then the size of Xn is either L to the power nd or n to the d, depending on which one you're working with. And let J be a kernel, defined on Xn cross Xn. That's rho of norm x minus y. Rho is like this. So it decays polynomially in the distance, and the exponent alpha is between 0 and d. Right. So when alpha is in this range, you look at Gn beta j. So Gn for the torus, Gn is just the graph on the torus, the random graph constructed on the torus. And when you're working with the space lambda n, Gn was the restriction of the graph to the ball lambda n. Now, if you take any fixed beta positive, then Gn beta j is sufficiently dense in the sense that the number of edges is of a higher order than the number of points. So to observe a phase transition, you need to consider beta c that goes to 0 as a function of n. So you can find beta c quite easily. So let zeta n be the unique positive number that satisfies this equation. So this is basically when the associated branching process becomes critical. So let zeta n be the solution to this equation. You can write it out in full for the torus and for lambda n. The exact equation is not so important, but from this, with some manipulations, you can show that zeta n scales like the volume to the power some exponent d minus alpha over. So consider the solution zeta n to this equation. So this zeta n scales like this, and then the claim is that the phase transition occurs in this model at 1 over zeta n. So if you look at this kernel 1 plus t j over zeta n, then for any epsilon between 0 and 1, any epsilon between 0 and 1, when you look at the kernel 1 minus epsilon times j over zeta n, then the size of the largest component is less than or equal to a constant times log n over epsilon squared. And when you look at the kernel 1 plus epsilon times j over zeta n, and the size of the largest component is at least of the order of the volume. So there is this phase transition happening around 1 over zeta n. So now I want to look at what happens around the point of phase transition inside the critical window. So to do that, let's define this kernel kappa lambda, which is j over zeta n plus lambda over volume to the 4/3. So this is similar to I had for Hierarch. For Hierarch, the critical window was given by the set of connection probabilities P of the form 1 over n plus lambda over n to the 4/3. So here we have j over zeta n, and there's a window around that of width 1 over volume to the 4/3. Then this is the result about the scaling limit for this model. If you look at, if you consider alpha between 0 and 5d over 6, this is the range of alpha for which we have this result. So here you look at the ith maximal components for each I, and again view them as metric measure places using the graph distance and the counting measure. Then if you scale the distance by volume to the 1/3 and scale the mass by volume to the 2/3, then again this rescaled metric measure spaces, they converge to the sequence of random metric measure spaces that I mentioned earlier, discrete. And again, here convergence is with respect to the Gromov-Foster-Perot topology, each coordinate, and the topology for the entire sequence, the convergence of the entire sequence is the product. In this sense, this model belongs to the Hierarchian universal. Now, convergence in the Gromov-Foster-Perot topology does not say anything, well, does not necessarily say anything about convergence of the girth or the existence of short cycles. So that has to be done separately. So to do that, let's define the surplus of a graph be the number of edges minus the number of vertices 1. So take any finite connected graph. Surplus is defined as the number of edges, the number of vertices plus 1. So for a tree, the surplus is 0. And let L lower circle be the girth, so this is the length of the shortest cycle, and let L upper circle be the length of the largest cycle. Then when alpha is between 0 and 2d over 3, here the range of alpha is again different. If alpha is between 0 and 2d over 3 and lambda is any fixed number in R, then the girth of each maximal component scaled by volume to the 1/3 converges to the girth of I lambda. So this was the ith matrix. Actually, I think my notation was mi lambda. So this is the ith matrix space in the sequence crit lambda. And similarly, the length of the longest cycle scaled by volume to the 1/3 converges to the length of the longest cycle crit I lambda for each I, and the joint convergence is with respect to the product topology. And also the number of surplus edges converges with the number of surplus edges. So in this case, there are no short cycles. So when alpha is between 0 and 2d/3, the girth converges to the girth, the length of the longest cycle converges to the length of the longest cycle after proper scaling. And also the surplus, number of surplus edges, they're also the same. For this model, unlike nearest percolation on the discrete torus, there are no short cycles. So this proof, for now, it only works for alpha between 0 and 2d/3. So what happens between 2d/3 and d? That's not clear at the moment. I say 3 results. So let me say a bit about the proof of the second one, the matrix scaling limit. So this proof has 2 components. So the first one is an upper bound on the 2-point function in the Brearley subcritical ratio. So we had fixed an alpha between 0 and d. In fact, for this one, alpha was between 0 and 5d/6. So we can pick any theta between alpha and d minimum to alpha, and define this new kernel kappa minus, which is 1/zeta n, rho norm x minus y. So this was just jxy minus volume to the minus theta/d. You subtract off this little bit, this pushes the kernel to the left, and it goes outside the critical window. So this is slightly subcritical. This is not purely subcritical. This is call it barely subcritical. And you look at the graph gn kappa minus. So now the kernel is kappa minus. This is a slightly subcritical graph, so barely subcritical graph. Let's define these 2 events. So x connects to y if there's an open path connecting x and y in this graph, and this x is connected to y directly by an edge. If there's a direct edge between x and y between x and y in gn kappa minus, then so then we have this upper bound on the 2-point function. Probability that 0 connects to x in gn kappa minus, it decays like essentially the connection probability when norm x is between 1 and volume to the some exponent. And after that, it's basically like this constant. Up to a constant is volume to this other exponent. Right? So this is like so if you could match, if you prove a lower, if you could prove a matching lower bound, this will be like a plateau. A similar behavior is seen when you look at nearest neighbor percolation, critical percolation, nearest neighbor percolation on the discrete torus, where the dimension is sufficiently high. This is a result by Hutchcroft, Dikta, and Gordon. And if you could prove a matching lower bound here, then this will also give you a plateau-like view here. So this bound on the 2-point function, this will in particular lead to upper bounds on these quantities. So this one is somewhat similar to the triangle diagram. The difference is that the last factor is different. So instead of being the connection probability, the direct edge probability. Similarly, the second one is somewhat similar to the bubble diagram. The difference is that the second factor is, again, instead of being the connection probability, it's the direct edge probability. So this bound on the 2-point function will lead to upper bounds on delta n and delta n tilde. So this is one component of the proof. And why are these bounds useful? This is because of the second part of the proof. We want to use a universality theorem. We want to apply a universality theorem to this model. Okay. To state the universality theorem, we need to introduce some notation. So suppose you have this finite collection of weights, x1, x2, xm, and you have this positive parameter q, and you can construct a random graph with gxq, where you have m vertices, and you place an edge between I and j with probability 1 minus exponential minus 2xi xj, and we do this independently for different pairs of vertices. And for any component P of this graph GXQ, let the mass of the component to be sum of xi. And similarly, you define CK to be the kth massive component of the random graph GXQ. So this is related to the multivariate coefficient. This random graph, if you view it as a process in Q, then the collection, the sequence of component masses of GXQ as a process in Q, it evolves like the multivariate coefficient. So two clusters with weights yi and yj, they merge at the rate of yi yj, and they become a new cluster of mass yi plus yj. So this is a multivariate coefficient with finite state space. So then for this multivariate coefficient, this result was proved by Aldous. So he showed that if you impose some conditions on this sum of xi to the power k and x max, these are the condition in Aldous' paper, then under these assumptions, if you look at the mass of Ci, so Ci was the ith massive component of GSQ, the sequence of masses converges in distribution to this C lambda, which is the standard eternal multivariate coefficient that I mentioned earlier. So this result is actually a bit more general than the result for Redosheni. So the result for Redosheni that I said in the first slide, then it follows from this one. It's the corollary to this one. So this result by Aldous, it gives you the mass scaling. So now we want the metric version of this. So to do that, what we do is we start with a collection of metric measure spaces, small metric measure spaces, let's say M1, M2, MM. And what you want to do is you want to put them together to construct a larger metric space. So you start with this collection of small metric measure spaces, and you have this random graph GXQ. You replace the ith vertex. You replace the vertex level I by the space Mi, where the junction for each junction point is chosen independently with probability mu I. Okay. So then this will give you a larger matrix space just by using the graph distance on GXQ and the metric on Mi. Right? And you can also put a measure on that. So this could be the measure. So this will be the measure. Yes, you just weight the measure mu I on Mi by xi. So then this will give you a larger random metric measure space. So let's call this G bar XQM. Then you define these quantities Ui, which is basically the average distance within Mi. And you define X mean, and this is the maximum diameter, and this other quantity tau. So we define these quantities and then impose some conditions on that. So this will give you control on the maximum weight, the minimum weight, the maximum diameter, and this tau that was related to the average distance within each Mi. So then this is a joint work. This is a joint work with Shankar Pamidi, Nicola Bhutan, and Shuan Wang, where we showed that if you have Aldous' condition, and in addition you have these stronger assumptions that on X max, X min, and the diameter, the maximum diameter, and this tau that are functions of this collection of small metric measure spaces. Then under these assumptions, if you look at the this Ci bar is the component of this larger metric space that corresponds to the ith massive component of GXQ. Then under these assumptions, you have Redosheni type scaling limit, or basically the component Ci bar. So here the scaling, the distance scaling will be this. So the second part of the proof, the first part was getting an upper bound on the barely subcritical two-point function. The second part of the proof would be using this universality principle, these two models. So to do that, again, recall that this was the barely subcritical kernel. And here we take M, so recall that M was the collection of small metric measure spaces. So we take M to be the components of Gn kappa minus, which is the barely subcritical graph. Then with this definition of, so with M defined like this, we establish this property, we establish the conditions that I stated here. So these and Aldous' condition. So prove those conditions with this choice of M, the components of the barely subcritical graph Gn kappa minus. So this is the part where the bounds on delta n and delta tilde. quantities delta and then the tan theta that are somewhat similar to the triangle diagram and the bubble diagram. They'll be needed here. So this is the bulk of the proof, proving this and just verifying these conditions for M. Then once you have that, you can couple the evolution from the barely subcritical graph chain kappa minus to the critical window, the critical graph chain kappa lambda. You can couple it with the multipoles. And then the universality principle, this one will tell you that the chi bar xq has the scaling limit crit, and then you get the scaling limit result for the graph that we're interested in. This one by comparison, just show that these two are very close in the gpsm. So that's the broad sketch of the proof. I stated a couple of other results, so I'm going to skip the proof outline for the results on the girth and complexity. So let me close with a few problems that are still open. So the scaling limit result that I mentioned, so this one only is the proof we have in this paper. This only works for alpha between 0 and 5d over 6. So this regime, where alpha is between 5d over 6 and d, you should still get the Rashenic scaling limit crit here. So that currently remains open. So one way to do it is to apply the universality principle, but you have to do you have to prove the barely subcritical estimates in a different way. Now, the same should also be true when alpha is between d and 4d over 3. So for the hierarchical lattice, this was conjectured in Hutchcroft's paper. And this should also be true for the discrete torus when the model is effectively high dimensional. So here alpha will be in some range depending on d. So when the model of long range percolation on the discrete torus one is effectively high dimensional, exactly when that happens, that also remains to be determined. So in that case, this model for the discrete torus that should also have the same scaling limit. Now, when alpha is between 4d over 3 and 2d, so here, as I mentioned in Hutchcroft's paper, there's a tightness results for the critical clusters. But the scaling limit is not known. So here, what should be the scaling limit in this regime when alpha is between 4d over 3 and 2d? So I mentioned some other non-Brownian universality classes. It could be one of those, or it could be something completely new. So the scaling limit for alpha in this range, so determining the scaling limit also remains open. And finally, the girth and complexity result that I mentioned, so there the proof only works for alpha between 0 and 2d over 3. Whether the critical maximal clusters have short cycles or not when alpha is between 2d over 3 and d, that also remains open. So if there are short cycles for alpha in this range, then that will be an interesting feature, because that will give rise to an intermediate regime where inside the critical window the maximum H probability goes to 0, but there are still short cycles similar to nearest neighbor percolation on the discrete flow. I'll stop here. Thank you.
Much. Are there any questions? Subhajit, any questions on the chat? Okay, let's thank Sanchayan again.